Okay, so I'm claiming that the parallel component of your A vector, again, you can think of it as acceleration, although if t isn't a time parameter, it's just an A vector, okay? So here's your unit tangent, here's your r double prime. Same picture I had here, except I don't have your r prime of t because I've already used it to get the unit tangent, right? And I don't want it because it gets in the way of labeling everything that I want to label, okay? So in this case, well, r double prime of t, you just project this back onto this line, and you get the component of r double prime in the direction of motion, which we call A parallel, but we'll also say that, well, what is the projection? And here's your theta, and it's going to be this times the cosine of theta. That's how long this side's going to be, right? Well, this times the cosine of theta is just its dot product with the unit tangent. Okay? Because the magnitude of the unit tangent is 1, then I'll write it out. Scalar projection on the unit tangent of r double prime, suppressing the t, right, is what? Magnitude of r double prime, magnitude of t, cosine theta. I'm writing that kind of small because it's a very straightforward calculation you've already seen. Unit tangent vector means, well, we got it by dividing this vector by its magnitude, so its magnitude is 1. That's why we call it a unit vector. That's why unit vectors are convenient. It's just magnitude of r double prime cosine theta, right? Which is the length of this side. Okay? Well, it's either the length of this side or the negative of the length of this side, depending whether theta is less than 90 or greater than 90. If theta is greater than 90, then it's going to be negative that. Clearly, in either case, when you multiply this by this, you get the component of your r double prime in your direction of motion. Okay? So what I'm going to call this vector now is, I called it A parallel, then I'm going to label it now R double prime parallel. Okay? And we can say, okay, that is A parallel because R double prime is your acceleration, right? Now, how do we get this vector? Because that vector is going to be your r double prime perpendicular, right? So, mixing up my color coding here. Here's your r double prime perpendicular, right? Or a perpendicular component of your acceleration, depending on your interpretation of the parameter. How do you get this?
Pythagorean theorem. Since you already know the other two sides.
How's that going to give you the direction? It's a good idea.
It'll
Good
give
idea.
you the magnitude.
Huh?
It'll give you the magnitude.
Yeah, but we got to know the direction because we got to know which side to put the stupid osculating circle on, right? Okay? Within this context, we got to know what the inward direction is in that curve. Okay? The direction that spins us out or the direction that takes us in. So we got to know the direction. Well, do you know r double prime? Have you now calculated r double prime parallel?
So
Well, how could you use those two vectors to get this one?
R double prime minus
Yeah.
R
Yeah, exactly.
parallel.
This plus this equals this, so this equals this minus this, right? Okay? So, okay, well, first of all, our double prime parallel then equals this, which is just this. Okay? I mean, this is the dot product, which is this, right? The dot product is this, which has been written out, right? It is magnitude times a cosine. So we write that as this, we get this, and now the two are equal. Okay? Work that out in whatever way makes the most sense to you. Well then, our double prime parallel plus R double prime perpendicular equals R double prime. So it's obvious from the sort of picture as well, but just to be sure, that R double prime perpendicular equals R double prime minus R double prime parallel. Okay? And then N is the unit vector perpendicular to motion and aimed at the inward direction, right? So R double prime perpendicular over its magnitude is a unit vector with all the properties I just mentioned. Now it's a unit vector, obviously, since you're dividing the vector by its magnitude. It would be if I use the right symbol for the subscript here, perpendicular, right? Okay? And since this is directed, it's an inward normal, this has to be an inward normal, right? Okay. So that's it. Now we've got our unit tangent and unit normal. And all we have to do to get a vector that defines the plane that we're in, or at least defines the orientation of the plane we're in, is take the cross product. Okay? I wrote T cross N, and I think it's N cross T, and I actually have to look to make sure. But, you know, my intuition is, if I'm going in this direction, no, that would be T cross N, never mind. I confused myself. Okay? My intuition is going in this direction, turning in this direction, the binormal is there, T cross N. And somehow I thought that was opposite to my intuition, because I can't tell the difference between opposites. Okay, until I check myself out. Okay, so we've got that, B equals T cross N, right? This gives you your unit tangent your unit normal, and this is a right angle, and your unit B, which is your binormal. That's a unit binormal. I didn't write the word unit because it's hard to write at the bottom of the page or the board, okay? But we know it's a unit vector. These three are unit vectors that temporarily define the plane of our motion and our direction of motion and the direction of our centripetal acceleration. Okay?